Done. You're done. Go. You can see. Try to see yourself there. There. Good. Okay.
No.
Go. You can start. Recovery zinc. This is the same smelter, same copper smelters, not the. Because we have a lot of zinc in a scrap recycling plant, which is a case study. This is not that, or this is smelter. What smelter it is?
Oh, I didn't understand the question.
Okay, it's a copper smelter, the dust, or it's from Gerdau?
No, copper.
Okay, good. Because in the the Gerdau case, you already have the study case. I sent it. Did I send it? No. We will have the whole engineering project, the Gerdau case. Okay, good.
But in the zinc side.
Yes, this is zinc. It's 40% zinc. And we have this XRD. We have the scaling up. We have the scaling up there, by the way. But the batch test. Also kinetic data. Okay, go ahead. Start, please.
Good morning, everyone. So me and my teammates, Ms. Jamila and
Okay.
Ms. Jamila and Ms. Isidora will present our project proposal entitled Recovery of Zinc from Copper Smelter Flue Dust using Waste Acid as Leaching Agent. So these are the contents for our project proposal: introduction, objectives, conceptual engineering, process diagram, mass balance, study cost, conclusion, and then recommendation. So what is copper smelter flue dust? So it is a byproduct of the copper smelting process where raw copper ore is heated to extract copper. So it is also considered as a secondary resource, and its treatment and recovery have been broadly investigated during the past decades. So CSFD is estimated to reach approximately 800,000 tons per year. It also contains valuable metals which we are interested to recover, and the traditional pyrometallurgical process, which we all know are very energy intensive, and now the current hydrometallurgical process method still faces challenges. Also, we are interested with the waste acid effluent. So it is also a co-product of copper smelting industry, which is produced during the flue gas desulfurization process. So this is the general flow chart for the disposal of waste acid. So first, sulfide precipitation, then lime neutralization, then sewage treatment, and then discharge. So for the discharge, the copper smelting industry is facing challenges since it generates a large amount of sludge and also faces conflict with meeting the discharge standards. So for the characterization of copper smelter flue dust, so these are the main elements found. So it contains copper, zinc, arsenic, cadmium, lead, and lithium. So our team found an opportunity since CSFD contain valuable metals. So we propose to utilize waste acid as a leaching agent, which can recover valuable zinc from CSFD, and then it offers a dual benefit, which is zinc recovery from CSFD and waste acid management. So these are the zinc market. So currently, it is used for chemical and petrochemical industries, ceramics, pharmaceuticals, agriculture, paints, and others. So in Chile, for the year 2022, $108 million in zinc minerals and concentrates, making it the 24th largest exporter in the world. The main importers of zinc in the world are Australia, China, Finland, Malaysia, and Colombia. So these are the types of zinc products: zinc carbonate, zinc sulfate, zinc oxide, and zinc chloride. So for our team, we are interested with the production of zinc carbonate. So it has drawn much attention due to its industrial applications, so such as agricultural industry, rubber production, paints and coatings, zinc, and also raw material for zinc oxide production. So these are the challenges for the zinc production, zinc carbonate market. So supply chain disruptions, product costs, fluctuation in zinc ore availability, and transportation disruptions. So now these are our objectives. We propose a clean technology to recover zinc from copper smelters flue dust, then to integrate waste acid as a leaching agent for zinc recovery, and then design a process and perform feasibility studies for production of zinc carbonate. So my teammate, Ms. Isidora, will continue the presentation.
Okay, the traditional process is in the left side. We have the CSO dust, and with waste acid, we leaching this material, and we have the left side, that is the process we choose. Then we have the cementation, precipitation of arsenic, and then the zinc and cadmium precipitation. In the right side, we have the conceptual engineering we elaborate for this assignment, and we have the same process, but we precipitate the zinc and cadmium first with sodium carbonate, and then we have the arsenic in solution that we also treat in another process, but we focus in the zinc and cadmium production. Okay, this is the process diagram. We have, like I told you, the leaching with waste acid. Then, and we have what's the name? Thank you. The tank with the bleached. Then we have the cementation with iron powder. And here we have two products. One is the sponge copper, and then we have the liquid that contains arsenic, zinc, and cadmium solution. This is our focus. Then, like I told you, we precipitate the zinc and cadmium with sodium carbonate, and then we have the filtration process. We separate the arsenic in solution, and then the zinc and cadmium. For the mass balance, we have a blank box that in the input we have 2.3% of zinc, and then in the output we have 0.6% of zinc. So we recover like 1.7% of zinc, and like I told you, we have some subproducts, that is the sponge copper, the arsenic in solution, and the zinc and cadmium in a tank.
Sorry for interrupt, but how much is the total amount of material? How many tons per year or the material? I think you...
In the
okay,
next
I'm sorry.
We are two. So, here.
Okay, so considering the cost for the project, we consider the capital cost and the operating cost. And the capital cost factors, we consider the equipment and machinery, the installation and cost, and permission and regulation, and investigation and development. Likewise, operating cost factors in this project we considered was the material cost, labor, maintenance, waste management, and quality control. But with the estimation, we considered a lithium carbonate project, which has similar tonnage production as our project. And then the capital investment that was used was like 10 to 60 million USD. And for the operating cost, it was 5 million to 20 million. So we used that for our calculation. And the electrical consumption at each stage of the process was also calculated, and these were the values. Because of time, I can't mention everything. But the annual CSFD production was estimated, we found it in a paper, was estimated to be like 800,000 tons per year. And considering the paper we reviewed, the recovery from the experiment was like 87.1%. So, and the grade 2 that was obtained was, the head grade was 14.3%. So we calculated an annual zinc production to be about 114.4 K tons per year. Then the annual recovery to be 99.6 tons per year. Now considering a price of zinc carbonate as 1.8 US dollars per ton, our revenue calculation was 180 million USD. And now considering the high end of cost, that is, if the operating cost and the capital cost was supposed to be very high, we estimated the net revenue to be like 100 million USD. But if the cost was supposed to be low, that is like 10 to 5 million, we estimated the net revenue to be 165 million USD. Any questions?
Lot. No. Just calculating the residence time. Not kidding. Okay, so let me for short things because we don't have too little time. So some tips. First, I can see. I know.
But okay, we
I can see myself. So just need to make an act.
We didn't do the scale up and all because
No, I know it was late. I understand that. I can see my face. Well, so when you start the presentation, we are going to present, reading. No. You always must keep the very intense connection to the audience to be attractive. Okay, so you are presenting a project to recover zinc from flue dust. We are converting waste in valuable elements. That we call it hook. And the hook will depend on the audience. If it is an investor, they want to know how much it is. So we are wasting 800,000 tons per year, and we have valuable elements, which 2.5% zinc, which is equivalent of a market of $1 million. That's it. This is a hook. That will be for an investor. For a researcher, it will be completely different. Again, we have 800,000 tons of material, which is very fine, 10 micron, which is attractive because it has valuable elements. You don't need to put money there. Valuable element or critical elements. Germanium, Indian, you mentioned critical element because the technical side understand that. They already know they are relevant. However, the challenge will be how to extract from very fine particles. And we are proposing a technology to extract it. Completely different topic. And then we have another audience. Can be environment, can be regulations. So the copper industry in Chile is very relevant, is 30% of blah, blah, blah. However, we have closed tube smelters and we are generating a lot of waste that is being accumulated and dangerous waste that contain arsenic. But this waste also contains valuable elements. So with this technology, we can extract the element and also remove the arsenic and stabilize the arsenic in an environmentally friendly way. You see same topic, three completely different ways to mention it. So always the audience is very, very relevant. Yes? You must be very clever, so you need to make an intention. You cannot do the three speeches at the same time. You will decide which one is more relevant. But during the presentation, you came up with the idea, the arsenic. So then the arsenic is very relevant, environmentally friendly technology. You came up with the idea later on. So, understand? But you cover, in the conference that we attended to Las Vegas, I have variety. I think I sent it to you, the presentations. Yeah, I think I sent it to you. So I talk about at the beginning of Chile policies, because, yeah, you see, you know that. Because they were talking about the relevance of having, for example, the keynote was the importance of having people engaged with environmental issues. Because they want to save the planet, and it's important to gather information of the people is interested in, for example, not using plastic bags. The willingness. And I say, but it's not more relevant having a policy, no more plastic bags. This is the only way to do it. And in Chile, in 2018, it was the first time in America, no plastic bag in supermarket. You don't have plastic bag in supermarket. No, you don't have plastic bag in supermarket. In Canada, 2018, they used very thin material, 50 microns. And then 2022, no plastic bag. America, forget it. They use plastic bags. It's discriminated. Okay, you know what I'm trying to say? So I came up with different things, different topic, because I detected the audience was different. And also I took these recovery fine particles, so I have a little information of flotation because they don't know. So I review the audience well in advance, their different background, so I need to prepare a different presentation for them. Yes, you do it for the audience, you need to study the audience. Yes, the last message is anytime you have a meeting, you need to gather the people. You need to look in LinkedIn, the activities, always. Okay, you got that. Now let's go to come back to slide, 11. Slide 11. Okay, good size, nice, you got the idea. Honestly, you don't need the picture, but it looks nice. Okay, it looks nice. You got the idea? No, you don't got the idea. Those are marketable products. Marketable products. Okay, next one, 12. 13. Okay, this is very important because if I take a picture from there, I barely can read. It is important, this very nice picture there. You remove all the images. All, and put in large number. Objective, propose clean technology with letters. It's better than this. They're not helping. Propose a clean technology is not related with that. Don't be confused to having a well-designed, nicer presentation with the proper message to the audience. It's one message per slide. Okay? It's good the content, but and again, if this is if you want to gather money for a proposal, emphasize the objective. If you are presenting a thesis, we will ask methodology. How are you going to achieve that? Okay, so it depends on the other. Next, let's come back to 14. You tell me about 14. Criticize 14. Criticize 14. Nothing. We can't read anything. So yes.
Probably it might be because of the projection size.
No. The general rule will be this size. The last this is a teaching from Professor Pérez and Professor Genaro. That actually is 50 years teaching. I'm good because I have good professors. If the last guy in the row can read, your presentation is good. And you don't need to have two things. You can do it later on. But the idea here is saying there are two processes. Okay, thank you. Mm-hmm. Simple. Just name it. Two processes. Then explain one.
Okay.
And then explain the second. But good, you are comparing processes.
Yes.
But separate things. So letter like this, and don't go into detail because people will be trying to. You require a lot of time to understand everything. So it's single message per slide. Okay. Okay, now technical stuff. Why you say that it's energy intense at the beginning? The smelting is energy intense. How does it work, the smelter? You say it's energy intense. Because you see something molten there, is it energy intense?
It is the traditional processes for treatment of CSFD are pyrometallurgy.
Yes. Pyrometallurgy, you say, if I'm wrong, you say is energy intense. Is that correct?
It requires a lot of.
Sorry?
It requires a lot of energy for the pyrometallurgical process. It requires a lot of energy compared to the hydro.
Yeah, could be. But pyrometallurgical process, it has self-heating. It's an exothermical reaction. The thing is, we're not using the heat generated. All the slag, molten slag, which is 1200 degrees, is being wasted to the environment, but it doesn't require energy, thermal energy. You ignite the reaction, and the reaction is exothermal reaction. You put oxygen, okay, as a reaction. You don't need to melt the things. That's what I'm trying to say. Do you know that? It's a combustion, exothermal combustion, and we generate a lot gigawatts of energy wasted that can be recovered. Okay, but okay, I know where you're going. When you put the ton of copper kilowatt of energy, I don't know. Perhaps you're right, but it doesn't sound good. The intense energy because it's self-ignite reaction.
Okay.
Don't say anything, and if you say something, put the number. The number would be
Okay.
per ton of cathode, not neither anode. Cathode copper, how many kilowatt hour? Don't say thing if you don't have the number to avoid any
Okay.
further question. You have the mass balance. Okay, come back. Last one, the mass balance. My mass balance with the compositions only is not good enough. You need to have the total amount to see we're talking about 1,000. Actually, I was calculating. Listen up. I was calculating 375 cubic meter per hour. So you're gonna be a huge reactor. Huge. If you put leaching
Yeah. We don't put the number like in the input and output because we don't in the next slide the numbers we put it's just estimated. So in the mass balance we put like the numbers we know that is involved in the
actually,
process.
I just explained today how to make the scale up. So just in case, review whatever number. I did the following exercise. I took the 800,000 tons per year divided by 8,200, which is operational running time. I don't know the solid content. I know it's fine particles, so that will be 0.2. Sorry, it will be 20% solid in best case scenario. Then you will have the total amount of pulp. I don't know the density. I made that a number, 1.3 tons per cubic meter. Then I end up with the cubic meters per hour. So it will be 375 cubic meters per hour. So it's gonna be big. You can divide that in three rows or 4 rows. You will end up with 20 cubic meter, 40 cubic meter reactor in order to estimate a rough estimate the cost. So always come to a rational number, come to liters per million. You have 30 liters per million, something like that. 1,000 liters per minute is big. You have to have the feeling how big is the equipment. Okay? You don't need to show that, is my advice, in order to check your numbers. But
yeah, like I told you, this is we don't put the numbers in the slide with the mass balance because we don't have the number for our process.
I know.
This number is just estimate.
I know, but you can say, I have no idea, but it's leaching process.
Yeah.
You can say,
this we use a project I make in the last semester in process design. So
yeah, okay. I'm trying to say something. You have no idea of the thing of the leaching process, whatever thing. You have the total volume. You can say leaching process hard. It can be 1, 3, 4 hours as the most. If it's more than this, forget about the process. As I mentioned, we have an application. 2 hours is fine, but the alternative is 300 hours. So forget it. It will be gigantic equipment.
okay.
So you can estimate all the time the size of the equipment. If you end up with 5,000 cubic meter, no, it's not possible to build it.
Okay.
So I'm talking about the roof of the things. And you say something. It's an estimate.
Yes.
Okay, estimate. You're estimating $1. Okay? So I'm trying to say, if you estimate, you put millions of dollars, thousands, round. Otherwise, it doesn't. And if you have the right number, if you have the precise number, never put that amount of digits.
Okay.
That's a good. You see from far away like ants moving.
So
Okay.
we have
Always,
to put like
yes. I mean, millions. And the important number, this number, this is the price. Okay, this is important. This is the important one. But put it in a different place. Okay, millions of dollars.
So wait, like the capital cost.
Yes, that is perfect. This is perfect. You don't need more than this.
Okay.
Remember, your certainty level is 50-80% uncertainty. So this number this is 60 times plus minus 30 times, and you're putting that here. It's a very common mistake for people who is professional. It doesn't look good.
Okay.
Never. There are two things. One, delivering the message. You confuse the people when you have too many numbers. Look, too many numbers. That can be, this is one slide, 4 slides.
Okay, so we have to put this number
No, this is fine.
and this number and that's it? Or
No,
We should just approximate them,
Yes.
not put them.
Usually have
okay.
3 digits. What do you think you do? 3 digits. This is for 4 slides.
Okay.
Deliver one message. Those are okay. And always it's good to having bars to show the relative size.
Okay.
But I think it's good effort. Just for to see what you learned today. Estimate the volume of the. Remember, you have 2 degrees of freedom. The number of parallel rows to reduce the size. Let's say one line. You end up with 5,000 cubic meters. No, we'll have 6 rows. And then you end up with 500 cubic meters. It's big, but just do the exercise.
Okay.
And again, you have the total solid tons per hour, and then you guess a number. Solid content can be that bad. 20%, 30%, 40% is the usual for leaching gold.
Okay.
I'll put 20. If I'm parting 40 will not work, you already know that. Let's take 20, we know it's not a real case. And then the residence time, K value, we don't know. But we know from autoclave reactor, for autoclave reactors, we know from leaching process, it will be 2-3 hours. In some cases it can be minutes, but 2-3 hours in order to determine where are we. Always try to estimate. Always. But I think it's good. Next one. We have to. And don't feel bad because my job is criticize you all the time to make better presentations.
Yeah.
And they're simple ideas. Go ahead. Sorry, the last thing. This is a sustainable engineering. What happened with cadmium and arsenic? Didn't mention you will end up with a process to have a stable form. Okay?
Yeah.
Whatever stream, it must be stabilized. Always. Okay, go ahead. Okay, I'll stop here. I will change the. Hernán, Eduardo, ¿alguna pregunta? Any question over there?
No, it's all good.
Hernán?
Everything okay?